Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. In today's topic, we will see the derivation of Lax wendroff technique, and we will see in detail why we will use Lax wendroff technique, and then we will see in detail this technique, how it can be implemented for other problems, and what are the limitations of this technique, and how to overcome the limitations of this technique. We will see in detail in this derivation. Fine. So here, basically, the Lax wendroff technique is an explicit finite difference method, so which is particularly suited for marching solutions. So we'll see what is explicit actually, and what is marching solution. We will see. So already we have seen what is explicit scheme and what is implicit scheme. So what is finite difference scheme? So finite difference method is a method where we will replace that partial differential term to the linear term in terms of index notation. So let's say we have a equation which is dou u by dou t plus u into dou u by dou x is equal to 0. So we have this equation. So for this equation, we have to do the finite difference formulation. For the finite difference formulation, these are two types. One is explicit, other one is implicit. For the explicit, we will have only one unknown variable and remaining all are known variables. So how do we write this one is? So u of I to the power of n plus 1 minus u of I to the power of n divided by delta t plus u of I into, so u of I plus 1 minus 1 minus delta 6 is equal to 0. So here you will have n, here you will have n, here you will have n. So basically what do we have? Whenever you have a term which is called power n, okay, so whenever you have a term called power n, that power n is nothing but the initial value, fine, and n plus 1 is nothing but your final value, fine. So here when we have given that initial value, so after computing these arithmetic operations, then we will get the final value which is u of I to the power of n plus 1. So here we have we have three parameters. Okay, so for the three parameters, one parameter is unknown and remaining two parameters are known values. So here number of unknowns are less compared to known values. So that is the meaning of explicit scheme. If you see implicit scheme, we will have more number of, so here you will get n plus 1, here you will get n plus 1, here you will get n plus 1. So that is the meaning of implicit scheme, where we will have more number of unknowns compared to known values. So therefore, Lax wendroff technique is an explicit finite difference method, and which is suitable for marching solutions. When we say marching solutions, the meaning is, so here when you have time derivative term, so with respect to time, the solution will vary actually. So that kind of problems are called marching solutions. When you see the steady state, let's say you have a Laplace equation, so where you have dou square u by dou x square plus dou square u by dou y square equal to 0. So basically this is called a Laplace equation. So for this Laplace equation, we cannot actually use these kind of marching solutions or this Lax wendroff technique. Okay, so that is the meaning of this marching solution, fine. And the perfect examples for the marching solution is the hyperbolic equations and the parabolic partial differential equation. So this steady state equation, or let's say this Laplace equation, which is dou square u equal to 0, is coming under elliptic equation. So therefore we can say that the Lax wendroff technique is applicable for elliptic, is not applicable for elliptic problem, and it is applicable for hyperbolic and parabolic partial differential equations. Okay, so this is what we have. Next, so here you can see the time marching solution of an inviscid flow using unsteady Euler 2D equation. So basically the time marching solution, as I told you, so whenever we say time marching, So the time derivative term or the unstudied term should be present in the equation. So when we see this equation, this is a continuity equation. So where inviscid and we say the compressible flow actually. Fine. So if we see the generalized continuity equation, we have dou rho by dou t plus you have del dot rho u equal to 0 actually. So if you take u bar this one, okay. So this del dot rho u, what is the meaning of del dot rho u? Del dot rho u, del in the sense what do we have? Dou by dou x of I cap plus dou by dou y of j cap. Fine. So this is what we have. Now this rho u, fine. So since we have this density term as varying with respect to time and space, then what we need to do, so we have to differentiate. So here what do we get? We get rho into u and rho into u. So we get this one. So therefore we need to apply the UV rule and get the details. So when you apply UV rule, so you can see rho is coming out and dou u by dou x. Next, so this term is completely of dou by dou x of rho into u. So this is what we have. So this term is completely dou by dou y of rho into v. So this is what we have. Right? Now this is continuity equation. Next we have x momentum equation. So in the x momentum equation, you can see that we have dou u by dou t term, fine, and you can see again minus u into dou u by dou x plus. So here you can see plus mu into dou v by dou y plus. So this is actually v into dou v by dou y plus 1 by rho into dou v by dou x. So this is what we have. Similarly, so this is actually u. Similarly, you have the unstudied term here minus u into dou v by dou x plus v into dou v by dou y plus. So here you can see. So here we have the pressure gradient with respect to y. Here we have pressure gradient with respect to x, since it is x momentum equation, y momentum equation. So from this, actually we can see that in each and every equation there is no viscosity term. So we have emitted the viscosity term by taking the inviscid flow assumption. So when these equations, let's take 1, 2, 3, 4, these 4 equations are coming under hyperbolic equations. Fine. So as I told you, when it's a hyperbolic equation, so what do we have? So the characteristic equation or the roots of this equation are real and distinct, in the sense real and unequal. So when we do the determinant and all the things, so we get two characteristic equations or two curves, so which behave in the realistic manner. Fine. So this is what we have. Now from these equations, so what we can observe, so all these 4 terms or the 4 equations, you can see the time derivative term with respect to rho we have, and with respect to u we have, with respect to v we have, and with respect to internal energy we have. So the variables rho, u, v, and e. E is nothing but internal energy. So the internal energy E is equal to Cv into temperature T. So specific heat at a constant volume into temperature. So therefore the density, u velocity, v velocity, and the temperature. So these are our flow variables. Fine. So these equations we are considering for deriving this Lax wendroff technique. Okay. Now, so let us take a density term. Fine. So what do we have actually? So we are taking this term actually, density term. Fine. So here when I say dou rho by dou t, I say that this is rho of I comma j to the power of n plus 1 minus rho of I comma j to the power of n divided by delta t. So this is what we have. Fine. So here you can see this term is the unknown term. So this is what we are deriving here using Taylor series of expansion. So this term is the known term or the initial term, okay, or the initial value or the initial term. So this is the term which is this term is the unknown term. Fine. Now that is what we are writing in terms of I comma j. So here n we can take it as so n we are considering it as t, and delta t is nothing but your 1. Fine. So when we apply this concept here, so that will be rho of I comma j to the power of t plus delta t. So which is equal to rho of I comma j t. So which is this is the initial value plus so dou rho by dou t dou rho by dou t into the delta t, the time derivative. Here it should be 1 factorial. Fine. Dou square by dou t square and I comma j into delta t square divided by 2 factorial plus so here we will write other term also. The other term is dou cube rho by dou t cube, okay, the power of t cube divided by 3 factorial plus so on we have, okay. So here you can see the mesh 2D mesh. Fine. Now this is the point of interest. So this is the neighboring point, this is the neighboring point, and this is the neighboring point, and this is the neighboring point. So this is point of interest P, this is A, this is B, C, and D. So A, B, C, D, basically these are the neighboring points. Fine. So P is nothing but our point of interest. Fine. So here what is happening actually? So the I comma j and I plus 1 comma j and I minus 1 comma j and I comma j plus 1 and I comma j minus 1. So these 5 points are the terms which are involving in one generalized equation. When we derive an equation which is of second order, so you will have these 4 terms, actually 5 terms, total 5 terms, including I comma j. So when we derive basically a central difference, we will have 3 terms. When we derive forward difference, we will have 2 terms. Fine. So basically when you take second order derivative, the order of accuracy is delta x square. When we take central difference, the order of accuracy is also delta x square. But when you take only forward difference, the order of accuracy is delta x. So that is the difference. Fine. Now the same concept we will apply for the remaining variables. So what are the variables we have taken? We have taken rho, we have taken u variable, we have taken v variable, we have taken the temperature. Fine. So for the previous equation we have seen for the rho. Now the same concept is applied for u velocity. Okay. So where you can see that you have u of I comma j t. This is the initial value. Dou u by dou t into delta t. This is the first derivative term, second derivative term, okay, remaining third derivative term. So if you want to go for higher order terms, then we will use that. Now next what do we have? Similarly v velocity. So v of I comma j to the power of t plus delta t. So this is the initial term or the initial value. So dou v by dou t into dou t. This is the first derivative term. This is the second derivative term. Fine. Next again now we have internal energy. So we can actually also replace this one in terms of temperature directly. So as I told you, E is equal to Cv into T. When you take the value of Cv as constant, so this one will change T of I comma j to the power of T plus delta T, which is equal to T of I comma j to the power of T plus dou T by dou T into delta T by 1 factorial plus dou square T by dou T square into delta T square divided by 2 factorial plus so on. So this is what we have. So we have u velocity, we have v velocity, we have temperature. Already here we have seen the density. Fine. Now these formulation we will use to substitute those values in the finite difference formulation. Here we will see in detail. Now you can see, consider density term. Your rho of I comma j to the power of t plus delta t. Here dou rho by dou t. This dou rho by dou t is nothing but our equation. The first equation. This is the first equation. Fine. This dou rho by dou t equation, we will discretize it. We will discretize it and then we will derive it. I will show you. So please remember, this dou rho by dou t equation is nothing but rho into dou u by dou x plus u into dou rho by dou x plus rho into dou v by dou y plus v into dou rho by dou y. So when we take the Taylor series of expansion formulation, this formula, we will substitute the value here. Okay, so that is what we are seeing. So what we have, so the dou rho by dou t equation, so if you take is equal to rho of I comma j, and we have this one as dou u by dou x. So what we are doing, we are taking the central difference formulation. Fine, the central difference formulation we have taken, which is u of I plus 1 comma j minus u of I minus 1 comma j divided by 2 delta x. Fine. Next, similarly, next we have this one as dou rho by dou x. So dou rho by dou x, again you have what, I plus 1 comma j and I minus 1 comma j divided by 2 delta x. Fine. Next, we have dou v by dou y, dou v by dou y. So we have I plus 1 and I minus 1 divided by 2 delta y. Similarly, we have dou rho by dou y, which is I plus 1 and which is I minus 1 divided by 2 delta y. Fine. So these are the equations which are coming under central difference scheme. Now what we are doing, so we have derived the density value at the next time level and using Taylor series of expansion, and then we substituted the continuity equation in the first derivative term, and we have written the central difference scheme for the values which we have in the continuity equation. Okay, so here if you compare, so this is what we have written. So we have replaced this dou u by dou x in terms of so here you can see the dou u by dou x is nothing but u of I plus 1 comma j minus I like u of I minus 1 comma j divided by 2 delta x in plus u into dou rho by dou x. So here you can see you have dou rho by dou x. What is dou rho by dou x? So here we have rho of I plus 1 comma j minus rho of I minus 1 comma j divided by 2 delta x. So the remaining terms are going on like that. Fine. Next, so if we want this second derivative term, so here what we are doing, so we are finding the value of density x next time level. So since we are dealing with the marching solutions, so the first term is actually substituted with the continuity equation. Now the second derivative term, here you can see it is actually getting by differentiating the equation 6.1. So this is the 6.1. So what we have, so this equation with respect to time again. So if we differentiate this one with respect to time again, so what do we have? So again we get this what you say, this will be dou rho by dou t, and again you have to differentiate, mixed derivative will come here. So that is what we get here. So you can see when we differentiate, we'll get rho into dou square u by dou x dou t. This is called mixed derivative, and dou u by dou x into dou rho by dou t. So plus u into dou square rho by dou x dou t plus dou rho by dou x into dou u by dou t plus rho into dou square v by dou by dou t. Next, plus v into dou square rho by dou y dou t. Next, plus dou rho by dou y into dou v by dou t. So these all terms are evolving. So how many terms we have? 1, 2, 3, 4, 5, 6, 7, 8. So these 8 terms are coming because, so if you take equation 6.1, so we need to differentiate. So here we have 4 terms. These 4 terms we need to differentiate with respect to time. So we have 2 terms here. Here, when you differentiate one time with respect to time for this term, you'll get 1. And again, we have to differentiate this term. That's why this term is getting into 2 terms. So that's why 4 into 2, we'll have 8 terms when we differentiate with respect to time. Now, so this is what we have mixed derivative. So how do we get mixed derivative is, so we will have to differentiate so the momentum equation with respect to time. Then we get the mixed derivative, which is dou square u into dou x dou t. Similarly, you have the mixed derivative of dou square v by dou by dou t. Now, what we have here, you can see, so for the 6.2, so here we need to differentiate with respect to x, here we need to differentiate with respect to y. So then we can substitute these terms in this equation here. So therefore, no, when we actually take only these terms, so we will have order of accuracy of delta t. When we actually include this term, we will have order of accuracy of delta t square. The main motto of the Lax wendroff technique is to have the order of accuracy of delta t square and have the order of accuracy of delta x square. That is why we are doing a lengthy numerical approximations. Fine. Now, when we differentiate the x momentum equation with respect to time, so with respect to x, so what happens is like here you can see dou square u by dou x square, dou u by dou x whole square. So plus v into v, again you are in mixed derivative here, dou x dou y. So for this actually you have to differentiate again the x momentum equation with respect to y. So these terms will come into picture. Fine. So when we see the full form of the mixed derivative equation, so this is the lengthiest formulation you can see. So this u is nothing but u of I comma j to the power of t. So this is second order derivative. So we know the formulation of second order derivative, which is u of I plus 1 comma j minus 2 u of I comma j plus u of I minus 1 comma j divided by delta x square. So this is what we have. So this is the formulation which we wrote. Next we have dou u by dou x. For this dou u by dou x, so what we wrote? So we have written the central difference scheme, which is u of I plus 1 minus u of I minus 1 divided by 2 delta x. This is what we have. Next v velocity into, so we have mixed derivative, so we have mixed derivative formulation. So the remaining things, they are like you can see the pressure of second order equation and the pressure of the first order equation and density of first order. So here we applied the mixed derivation formulation. Here we applied the central scheme. Again here we apply central scheme. Here we apply the second order finite difference formulation. Then you can see again we apply here a central difference scheme. So here you can see this is the central difference scheme. This is the central difference scheme. So here you can see this is the second order scheme. So we know the basic formulation. With that basic formulation, we are applying those formulation for these values, and we are getting a lengthy expression. So this thing we need to substitute there in the density equation, where here we have to substitute. You can see how lengthy it is. So the Lax wendroff technique has a very lengthy mathematic approximation or formulation. Fine. So the remaining thing again. So if you want dou square rho by dou t square, so we are replacing this. Again we need to replace this. Again, so these are very straightforward. Dou u by dou x, dou rho by dou x, dou v by dou y, and dou rho by dou v. So here you can see the other terms which are second order derivative, mixed derivative terms, they are very actually lengthy equations. So the remaining, so we have done for this already. The remaining terms, dou square dou by dou x dou t, dou square v by dou y dou t. So these kind of lengthy expressions. So only this one term we are substituting here. Imagine when we do the same analysis for this one, so for the four terms, so you can see a very lengthy equation. Fine, that lengthy equation actually will make so many number of variables, so much amount of active mathematics. Fine, so therefore what we can say, the Lax wendroff technique is a technique which has a higher lengthy mathematical approximation to get the second order derivative term. Fine. So here, what do we have? So we know we are finding this. We know this is initial value. We know this is from the continuity equation. We have done this actually. So with this, we will get the value of delta t square. So what do we have? So we will have to repeat. This is for only one iteration. So this one iteration, you can see how much length of mathematics is there. You can see. So for the next iterations, so it will keep on repeating for the next variables. Next variables in the sense. So here we are taking I comma j. Next we have to go for I plus 1 comma j. Next we have to go for I plus 2 comma j. Or if you want to see for I minus 1 comma j. So at all grid points, you need to see actually. Fine. So here you can see how the time varying grid thing is happening. You can see. So since it is explicit scheme, so this is the only one unknown variable we have. So these are the known variables. Okay. So this one is coming at n plus 1 level, or you can say this is t plus delta t term. Fine. So from this figure we can see that. So what do we have? So the time and the x coordinate. So when you see the values of x and y coordinate, when you see the values of I comma j, so this is one plane, so which is of plane t, or which is of initial plane, or the plane with initial conditions. Okay. Next we have the other plane, or the plane above this, so which is of t plus delta t, or which is of n plus 1 plane, or which is of the next plane or the higher order plane. Fine. So this is what we have from the time derivative, which we can see explicitly from marching from one solution to other solution. So this is t plus delta t. When you see t plus 2 delta t, what happens? You'll get a other plane here, and these values will be a known values at the time. Here you will get one unknown variable again. So like this, so to show a pictorial representation, so I have done some small plane arrangement where this is the initial plane with the initial values. This is the second plane or the unknown plane where we will calculate this unknown value with respect to this initial value. Fine. So this is for the marching solution. Okay. Now the procedure, whatever we have seen for only the row of I comma j t plus delta t, we have seen, but we have to do the same procedure repeatedly for the u of I comma j t plus delta t, v of I comma j t plus delta t, e of I comma j t plus delta t. Okay. So we are repeatedly doing the same task for the other things. Fine. So here t plus delta t is nothing but what? So our next or the unknown parameter. So the same aspect we have to do for u velocity, v velocity, and internal energy, where indirectly we can say that it is temperature. Now why we are doing this? So in order to get higher order accuracy value, so we are doing this actually. So Lax wendroff technique is having a accuracy, order of accuracy of delta x square or delta t square and delta x square. Fine. So this is what we have. So the Lax wendroff technique is a technique which is very lengthy in mathematics and very lengthy in deriving from one variable to other variable, or let's say one mixed derivative to other mixed derivative, and we are doing for only at one point. When we want to calculate for all the points, so it is a hectic procedure, right? So with this, we have seen the detailed explanation of Lax wendroff technique, and here the major limitation is the derivation of the unknown variable for higher order accuracy scheme is very lengthy. For calculating only density variable, so we are getting a 2-3 pages of derivation, only one density variable. Similarly, we have to do for velocity. Similarly, you have to do for v velocity. Similarly, you have to do for temperature. So you can imagine how lengthy it will become when you do for the full length of equations. Fine. Though we are getting higher order accuracy, but the arithmetic operations and evaluating the parameters are very hectic. Fine. So the limitations of Lax wendroff technique can be overcome using McCormick's technique, where you'll be doing the time averaging of the both central difference schemes. So that we will see in detail in the next module. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.